Hi, everyone. Welcome to today's research talk. Our speaker today is Siddharth Garg. Professor Garg received his PhD in electrical and computer engineering from Carnegie Mellon University, 2009, and a bachelor's of technology in electrical engineering from the Indian Institute of Technology in Madras. He's currently the Institute Associate Professor of ECE at NYU, Tandon, where he leads the Ensure Research Group. His formal designated research interests are machine learning, cybersecurity, and computer hardware design. And you can see the talk title there on the slide, so I'll just hand it over to you.
Thank you, Jonathan. I'm really happy to, excited to talk to all of you. And, the one thing I will say is that I understand that it's a relatively diverse audience. And in fact, I think that especially in applied crypto, there's a growing number of people who are interested that come from a range of backgrounds. My own background actually is in hardware. So, the reason I'm bringing this up is if there's anything that isn't clear at all, either from a crypto standpoint or a machine learning standpoint, please feel free to interrupt. I would prefer for this to be as interactive a session as possible. And then the other thing I'll point out is much of this is the work of my former PhD student, Zara Gotzi, who is currently a postdoc at UC San Diego. So you really, all of the credit. If you like the work, it's because of her. If there's something you don't like, you can pin it down to me, all right? Okay, so with that, let me begin. Hopefully, I don't have to really motivate why machine learning and especially deep learning has had significant impact in the real world in the last few years. We've seen applications that range from autonomous driving to medical applications, for example, cancer detection from histopathological images, and even kind of interesting applications like playing the game of Go. And very recently, an AI system, AlphaGo, was able to outperform and defeat Lee Sedol, the world's best Go player at the time. So, we are seeing this diverse set of applications for deep learning, and this has been enabled essentially over the last several years by improved hardware infrastructure. In fact, deep neural networks are fairly computationally expensive to train, and the fact that we now have modern GPUs has made it possible to train these massive deep networks that sometimes perform fairly amazing feats. But in addition, there have been algorithmic improvements and the availability of massive amounts of data. Now, hardware infrastructure and the availability of large amounts of data also create some challenges. In particular, these are not accessible to all users. And we are, in fact, increasingly seeing even a divergence between academic research and industry research, because industry has access to more compute and more data than academic researchers have. And this creates a fundamental, or I think a basic problem of outsourcing. And so the outsourcing problem is the following, right? So now you can think of essentially a client-server model. The client is a computationally constrained device, say a mobile phone, and a cloud server that has, for all practical purposes, infinite compute and infinite storage. And for that reason, a client device might want to outsource. For now, we'll just talk about deep learning inference. So they might want to outsource deep learning inference to a cloud server. Essentially, they would send to the cloud a deep model and an input and receive a prediction result. And of course, as I said in the previous slide, there might also be settings where the client does not have the computational resources to train the model or enough data to train an accurate model. And in this setting, you can imagine also that the cloud server not only has computational resources, but large amounts of training data using which the cloud has trained an accurate deep network for some sort of inference task. And so in this setting, the client would send to the cloud just an input and receive a result in response, but really wouldn't necessarily see the model that is being used to perform this sort of inference. Now, these two examples raise questions both of integrity and of privacy. So on the one hand, how can the client be assured of the integrity of the results that the cloud provides to the client? And a malicious cloud or a lazy cloud might have incentives to provide incorrect results of computation. It also raises questions of privacy. In many settings, the client might have sensitive data that it would like to get inference results on, for example, health data. And in this case, the client may not want that input to be revealed to the cloud, but really does, of course, want an inference result on their, for example, medical images. Okay. So today we will discuss both the privacy and integrity questions. We're going to use crypto to enable solutions to these problems. I'll actually spend a lot of time looking at the privacy question and then conclude with some discussions on how integrity can be enabled in this setting. But before I proceed, can I just get a quick sense of whether the problem setup makes sense? Okay, so can these untrusted parties collaborate, and can they particularly collaborate in the context of deep learning inference? That's a question that we're going to ask. We're going to answer, as I said, this question by using tools from our cryptography toolkit. These include tools like secure multi-party computation and homomorphic encryption that allow for computations on private data. And for integrity, we'll be using cryptographic tools from the domain of verifiable computing, where two parties, where computation can be outsourced to an untrusted party, and the untrusted party in return can convince, in this case, a verifier that the computation has been correctly performed. Okay, so our goal will be, how do I use these tools that are reasonably well known in the crypto community, but apply them to the problems that I described in the previous slide that relate to outsourcing of deep learning inference. Now, the challenge here is that despite several, arguably decades of improvements in crypto protocols, applying cryptography to deep learning, at least naively, results in impractically high cost. So on the one hand, you expect, for example, deep learning inference to operate in real time, potentially getting hundreds of inference responses every second. And on the other, if you try and apply, well-known crypto techniques to deep networks, you end up in, several orders of magnitude blow up in compute, and that results in essentially impractically slow systems. So the question that I really want to answer in this, or at least make a step towards answering in this talk, is how do we make these systems more practical? And we're going to do that with the same kind of philosophy that's going to permeate through this talk, which is to co-design the crypto protocols and deep learning architectures, let's say. And the reason for kind of co-designing these crypto protocols and deep learning architectures is because thus far, deep networks have really not been considered or thought of in the context of crypto. And so much of the deep networks that we know of and use are really optimized for what I would call plaintext inference. And I'm going to show you that crypto costs can be very different from plaintext costs. And as a result, there is a need to rethink what deep network architectures look like, given that we know that we'll be deploying these crypto protocols. And at the same time, yes.
So what's stored in the blocks versus, what kind of data do you store in the blocks? Are you talking about model parameters or algorithms? What's in there?
Right, that's a great question. So let's go back, and I'll make that more explicit actually in a couple of slides. But essentially the block is, you have two parties. The block we will think about in the privacy setting is one party has a model. The algorithm is known upfront. The only thing that is unknown, or in some sense, the server stores, is a deep network and its trained parameters. So in fact, even the architecture of the deep network will be assumed to be known. What is unknown to the client are the weights of the deep network that are typically the asset of interest, because these are kind of, the result of fairly time-consuming training. And on the at the same time, from the client's perspective, what the client wants to keep private is its input.
Yeah, so like during training, let's say you'd start off with random weights stored in the blocks, and then after an iteration of training, you'd have updated weights stored in the blocks, that kind of thing?
So excellent question. So one thing I perhaps should have clarified upfront is that everything I'll present today relates to inference. So I'm currently, and there's a huge kind of body of work and essentially a problem domain where you want to train deep networks privately, for example. but we will assume that the training has been performed and we'll be talking about the inference problem only.
Okay, cool. Thanks for that. Yeah.
Thank you. Yeah, I'm glad that you asked the question. I think that deserved clarification. So going back then, our goal would be to co-design crypto protocols, keeping in mind deep learning architectures, both, and I'll show you examples of how deep networks can be optimized, keeping in mind the special properties of crypto protocols, and also some examples of how you can update crypto protocols, keeping in mind some special properties that deep networks have. Okay, so I'll kind of hopefully show you both the yin and the yang. So the first problem that I want to address is essentially the privacy problem for outsourced deep network inference. And again, I think, let me kind of underline the word inference. We will assume that the server has a trained model that it has trained at large expense on its own private training data, but the model has been trained, right? The model architecture is known to everybody. So how many layers, the parameters of every layer and so on. But what the server wants to keep private are the weights of the model that are the asset of interest. A client wants to obtain an inference result on this private model that the server possesses, provides an input to the server, gets back a result, and the client would like to keep its input private. As I said, this input might contain sensitive data like health information. And so the first problem is, how do we enable this? How do we enable secure outsourced deep learning inference, where the server gets to protect its asset, which is essentially a trained deep network, and the client gets to protect its asset, which is whatever private input it wants to get computational results on or inference results on. So for this, I'm going to kind of go and pick out tools from my cryptography toolkit. And in fact, these are not tools that we have developed, but have really been developed in the literature, some kind of outstanding prior work. The one that we will build on specifically is called Delphi. And very briefly, let me kind of explain to you how Delphi works. So you can think of a deep network as multiple layers of computation. The red layers essentially perform linear operations, matrix multiplications and convolutions. The blue layers perform nonlinear activations. In particular, for this talk, I'll be interested in ReLU activations, which are the most commonly used activation function in deep networks. And a ReLU is nothing but a rectification operation. So if the input is negative, the output equals 0. If the input to the ReLU function is positive, the output equals the input, okay? But it is a nonlinear function. And as it turns out, nonlinear functions are, arguably more challenging for a lot of the crypto protocols that have been developed to deal with. As a result, what Delphi does is that it uses actually two different protocols, a different protocol for these linear layers, right? The protocol essentially, again, perhaps for the sake of this talk, the details of the protocol don't matter as much, but essentially it uses secure multi-party computation for the linear layers. And then for the non-linear ReLU layers, it uses what is called a garbled circuit or GC protocol. Now, the interesting thing is that when you compare the relative costs of cryptographically computing linear layers versus the ReLU function, there's a massive difference, a roughly 4 orders of runtime difference between kind of the cost of the garbled circuit protocol versus the cost of secure multi-party computation, which is what we do for the linear layers. Now, one thing I want to be very careful about is that when I say runtime, I actually mean online runtime. All of these protocols actually perform a lot of offline work that is independent of the actual input that is being processed by the deep network, and therefore that offline work can be performed in advance. So we are going to be interested in comparing the online costs of these protocols. And as I said, in terms of online cost, the ReLU functions are several orders of magnitude more complex, right? Or at least take several orders of magnitude more time to compute than the typical linear layers in the deep network. Now, why is this interesting? This is interesting because if you think about how conventional deep networks have been designed, they're really designed to minimize the number of multiply and add operations. The reason is ReLUs, essentially these comparison operations, are really trivial to perform in terms of computational cost in plain text, right? The real cost is incurred in the number of multiply and add operations that are incurred in the linear layers of the deep network. And consequently, you'll often see in deep learning papers, pictures like the one that I'm showing you here, that on the y-axis, I'm showing you accuracy, and on the x-axis, I'm showing you multiply and add operations. And typically, deep networks will be optimized to achieve the maximum possible accuracy under some budget on the number of multiply and add operations, under some computational plain text budget. Okay, and in fact, like several years of research in deep learning has looked at searching for efficient architectures that operate at low multiply and add operation budgets. But because of the data that I showed you on the previous slide, or the trends that I showed you on the previous slide, for cryptographic inference, what we care about are the number of ReLUs in the deep networks. In fact, linear layers and the number of multiply and add operations have a very small contribution to the overall online cryptographic cost of the deep network. And consequently, what we'd like to do is to look at the trade-off space between accuracy, again on the y-axis, versus number of ReLUs, not the number of multiply and add operations. And what I'm going to show you is that if you look at conventional deep network architectures, they really are not optimized for ReLU counts. Nobody cares about ReLUs for conventional deep networks. And consequently, if you just use these deep networks, off the shelf, they have relatively high ReLU counts and are quite inappropriate for cryptographic use cases. All right. So my first kind of part of this talk will be trying to figure out how do you redesign deep network architectures, keeping in mind our new constraint that really cares more about ReLUs than multiply and add operations. Okay. Any questions about this kind of broad motivation thus far?
Yeah, it just was unclear why ReLUs would be so difficult to compute in the cryptographic setting, because they're so easy, really, to compute normally.
Yeah, so that really kind of, I would have to delve, and I'm happy to offline, right, into the details of these crypto protocols. But maybe the top line argument that I can give you that hopefully might be convincing is that, the way you represent values in the crypto world for the linear layers is you just kind of represent them as floating point values, both the weights and the inputs, kind of almost essentially do effectively what you would have done in the plain text world for the linear layers. Now, when you try to compute ReLUs, you have to switch to what is called this garbled circuits protocol. And a garbled circuit takes whatever nonlinear function you're trying to compute, and it really kind of represents that nonlinear function as a Boolean function, as a Boolean circuit of logic gates that operates on bits, on individual bits. So what you're doing is you're taking these inputs, which let's say it's a 32-bit input, and you're kind of implementing a comparator as a Boolean circuit with potentially thousands of gates. And each of those gates to evaluate cryptographically requires multiple encryption and decryption operations, right? So it's really this kind of representation that's being switched on the one hand when you're doing linear layer computations, you're performing, at least online for this protocol, you're essentially kind of doing what you would have done in the plain text world. But for ReLU layers, you just kind of have to do this extra work at the bit level. Okay, so I mean, I don't know if that is particularly convincing, but that's the best argument I have at this level of abstraction. Yeah, no, it's interesting, but carry on, yeah. All right, so what I'm going to show you is if you take a standard deep network, I'm going to show you three, and I'll make it reasonably, I think, hopefully quick. I'm going to show you three operations. We call them ReLU shuffling, ReLU pruning, and ReLU balancing that can be applied to any existing deep network architecture to actually optimize that architecture, keeping in mind that ReLUs have suddenly become so important, okay? And I'll kind of explain to you how each of these optimizations work. And then I'll show you how, from a large design space of potential architectures, you can pick the architecture that has the highest accuracy for a given budget in terms of number of ReLUs. Again, keeping in mind that my runtime is dominated by the number of ReLUs in the deep network. So let's talk about each of these optimizations first, and then I'll kind of talk briefly about the architecture search strategy. The first optimization is ReLU shuffling. This is actually relatively straightforward. So one of the key operations or one of the main operations in a traditional deep network is what is called a skip connection. So I'm showing you an example of how you perform a skip connection in ENAS, which is one of these large or very successful deep neural network architecture search frameworks. Now, what does ENAS do? It takes data from one of the layers of the deep network, let's say layer 0, and forwards that information to a subsequent layer, for example, layer L2. Skip connections are extremely important. They've been shown to improve the performance of deep networks, both because they allow for more efficient optimization during training and because you can introduce more trainable parameters into the network. You can essentially improve the capacity of the model to learn information. Okay. The way that ENAS introduces a skip is that it takes information from layer L0, kind of forwards that information. You can see that here to layer L2, and then it concatenates, the information that already existed at the input of layer L1 with this new forwarded information, performs another set of ReLU operations, an additional set of convolution operations. These don't matter, and that gives you the new output in layer L2. Now, if you think about these skip connections that are being added, every time you do a skip, you're actually introducing additional ReLU layers. Now, for the folks who designed ENAS, they didn't care. As I said, ReLUs are basically free for plaintext inference. So essentially, I would argue that ReLUs were being kind of indiscriminately scattered around in these networks. And our first observation was, once you start caring about ReLUs, you can do relatively trivial things that result in large reductions in ReLU count. So one trivial optimization that we call shuffling basically observes that, look, if you take the output of layer L0, forward it to layer L2, and then perform a ReLU operation, well, the ReLU operation is being performed anyway in layer L0. So instead of forwarding L0, I can forward the ReLU'd version of L0, and I can essentially remove an additional large number of ReLUs that I've suddenly introduced into the network. And so this is essentially a functionality preserving operation. It's just keeping in mind that the moment I start caring about ReLUs, I can start kind of moving these things around to optimize the ReLU counts in my network. So this automatically kind of actually results in a 4x improvement across many of the architectures that we played with. All right. So this is relatively trivial. As I said, this is mostly coming from this kind of reimagining these architectures from a ReLU perspective instead of a flop perspective. The other thing you can do is actually you can start pruning the new ReLUs that have been introduced in the skip connection. In fact, the primary goal of a skip connection is to forward information from earlier layers deeper into the network so that information can be used in making predictions. And the fact that you're adding a ReLU layer really doesn't that information is being forwarded, the goal is being achieved, the ReLU really doesn't matter that much. And I'll show you that that's actually the case empirically. And so we actually prune away this extra ReLU that was added in the skip connection as well. And now this is the interesting part. We've introduced this new architecture where skips are essentially free from a ReLU standpoint. So every time I add a skip connection, I'm adding new trainable parameters into the network, but I'm adding 0 extra ReLUs, right? And that's going to be critical. The fact that skip connections are now free. In the original ENAS and many other frameworks, skip connections introduced tons of extra ReLUs into the network. And it turns out that those ReLUs can either be reshuffled without changing functionality, or can just be pruned away without incurring much loss in accuracy. Okay, so these kind of modifications, and this is again going to be important, allow us to introduce skip connections anywhere in the network, and those skip connections are going to be free for us, at least from the standpoint of ReLU counts. Okay, I'm going to make use of that property later. All right. The other thing that we noticed when we were kind of thinking about these networks from a ReLU perspective is almost every neural network architecture, at least convolutional neural network architecture that I know of, has the following kind of properties. So these network architectures operate on three-dimensional tensors, and every layer of the network takes as input a tensor and outputs a new tensor that can have a different shape. Now, typically, as you go deeper from one layer of the network to the next, you end up reducing the spatial dimensions of your 3D tensors. Those spatial dimensions are what I'm calling the H dimension, typically by a factor of 2. And in return, you typically increase the vertical dimension, the number of channels in these tensors, which I'm calling C, also by a factor of 2. And it turns out, if you dig deeply and look at some of the original papers, this is done to preserve the number of flops, number of floating point operations that every layer is performing. It turns out actually the number of floating point operations that a layer performs equals the height square or spatial dimension square times the square of the number of channels. And therefore, if you're kind of reducing H by a factor of 2, it makes sense to increase C by a factor of 2 to preserve the number of flops across layers of the deep network. And you can actually show that this strategy maximizes the number of trainable parameters under a given flop budget. And why does a flop budget matter? Because, well, flops are what dominate the plain text cost of deep learning inference. So actually, it turns out to be the optimal strategy if you care about flops to increase or maximize number of trainable parameters. But we care about ReLUs. And the number of ReLUs in a layer of the network is actually proportional or equal to H squared times C. So if you're going to reduce the spatial dimensions by a factor of 2 going from one layer to the next, to preserve the ReLU counts across the layers, we actually should increase the number of channels by a factor of 4, not by a factor of 2. And these result in basically slightly differently shaped networks where the number of channels actually grows much faster as you go deeper and deeper into the network compared to a conventional flop balanced network. And we can show in their results in the paper that establish that if your goal is to maximize the learning capacity of the network under a ReLU budget, then this strategy is actually optimal, right? And again, when I say learning capacity, for now, we'll just say that learning capacity is proportional to number of trainable parameters.
Does this mean that using a blockchain to store your data or your parameters kind of dictates what kind of networks you want to deploy?
In as much as you care about the size of the data that's stored in the blockchain, right? And I think, in fact, what I will show you is these ReLU balanced networks are massive in terms of number of parameters. So in fact, the storage cost of these networks is a lot higher than the storage cost of an equivalent flop balanced network.
Okay.
But again,
I have this
not storage cost, but it's really inference time.
Or do I have this wrong? Is that somebody designs the network outside of the blockchain, and now you're taking that network and implementing it in the blockchain?
So I think that's perhaps the
right. That's where we're going first.
Right,
and so
right. So
this
we're
really
only
just
looking at
dictates the
problem.
architecture. It doesn't matter how you design your network.
Correct.
You're going to take it through this engine and de-ReLU it or change the ReLU profile. Okay.
Yeah, or you could actually train them from scratch, keeping in mind these new architectural structures. Right. So we're not really taking existing networks and kind of de-ReLUing them. We're just kind of training them from scratch, actually. And in this case, I mean, there is no blockchain really in any of these. So it's not immediately clear to me how the blockchain is related, right? We're just thinking about a simple client server setting. There may or may not be a blockchain involved. And so the final thing I'll point out is that, what is nice now is that you can essentially take what we call the skeleton or base networks that do not have any skip connections. And you can try to optimize first the accuracy versus ReLU trade-offs of these base networks. And there are ways to do that, which I won't discuss today. And so you get this kind of trade-off curve between accuracy and number of ReLU counts for these base networks without skip connections. And what did I tell you? I said, the way that we introduce skips, those skips actually don't increase the ReLU count of the network. So then we're going to try and figure out where to add skip connections in the network to further increase accuracy over and above these base networks. And in each of those cases, we'll get these vertical improvements because we're not increasing ReLU counts. We're just getting more accuracy. And therefore, you're going to get a Pareto curve, right? Trade-off between accuracy and number of ReLUs that's improved as a result of these free skip connections that we add. Now, this question of where to add the skips, that itself is an interesting problem. We leverage prior kind of architectural search techniques, which I will not go into detail here. But again, I'm happy to talk about these offline. But I just wanted to kind of conclude a little bit this part of the talk with some results. In all of these charts, I'm going to show you x-axis is number of ReLUs in millions, and the y-axis is accuracy. This is for the CFAR 10 and CFAR 100 data sets. And you can see the base network accuracies are shown in red, and then after ReLU shuffling, you can actually get more accuracy for the same number of ReLUs, or get 4x reductions in ReLU counts for the same accuracy as I had promised. And then this additional pruning strategy that I described actually kind of gives you the trade-off curves shown in green. And you notice that actually pruning sometimes gives you lower accuracy compared to just the shuffled networks. But pruning and shuffling together do give me this benefit of free skip connections that I'm going to leverage later, right, to optimize my network. So we're going to stick with these pruned and shuffled optimizations. Okay, and the key, so this is actually showing how much better ReLU balancing is compared to the original flop balancing strategy. So if you look at one of these networks, let's say CNET C100, which is in the second row, notice that you get 68% accuracy after ReLU balancing versus only 64% accuracy for the conventional flop balanced networks. And the result is that our ReLU balanced network, and the reason is that our ReLU balanced networks have 4 times as many parameters, 1.3 million parameters, versus the original flop balanced networks that have only 300,000 parameters. So this extra learning capacity is allowing you to increase accuracy from 64% to 68%. And now when you put all of these optimizations together, you can start looking at kind of the Pareto curves in terms of, again, test accuracy on the y-axis. And on the x-axis, I'm no longer using a ReLU count. I could have, but I'm actually plotting the actual online runtime of cryptographic inference. For our proposed networks, which are shown in red, they're called CryptoNAS, right? And then there's a bunch of comparison points, including traditional res nets, mobile nets that are actually optimized for flop counts, dense nets, and other architectures. And what you observe is, these CryptoNAS networks actually always on the Pareto boundary and perform, either give you significant accuracy improvement over state of the art, or for the same accuracy reduce online runtime by between 2x and I think 2 and 4x or something like this. There's one data point which actually is kind of interesting. This is a data point from Delphi. Maybe you can see it here. It's this data point here, where actually this Delphi data point does better. And again, I'm happy to talk about this offline. Delphi actually, what it does is that it replaces ReLU activations with y equals x squared, with quadratic activations, for which you do not need garbled circuits at all. And as a result, they get all of the improvements using this alternative method. So one of the Delphi networks actually is better than CryptoNAS. The other networks, CryptoNAS performs better. But subsequent work, which I'm not going to talk about today, we are able to actually significantly outperform CryptoNAS itself and outperform all of these Delphi networks also. Although, again, this is now a pretty active area of research, and there are papers, every kind of ML conference and security conference. So maybe we are not the state of the art anymore. I think we were last month, but that might have changed. That's really what I wanted to say about designing deep networks, keeping the crypto protocol in mind. I'm going to briefly talk about a paper that appeared a couple months back at NeurIPS 2021, where we actually also look at a few protocol modifications, keeping in mind properties of the deep network. Okay, so again, before I proceed to that work, this is a paper called Circa, or arguably a protocol that we call Circa. I just wanted to see if there are any kind of questions about CryptoNAS and kind of this idea of redesigning deep networks, keeping in mind crypto costs. Another property that machine learning workloads that deep networks have is that they're reasonably resilient to small errors. So when I'm performing, for example, inference computations, or even during training, if I take some values, in fact, even a reasonable fraction of values, and kind of arbitrarily set them to 0, the accuracy of the network does not really suffer. In fact, many deep networks are trained with a strategy in which randomly selected values in the network are zeroed out. This is called dropout, and it's actually a regularization technique. So deep networks tend to be reasonably resilient to these types of errors. Now, thus far, all of the crypto protocols are designed to match exactly the plaintext computations. But as I'm pointing out, occasional errors in plaintext computations are acceptable. So how can we think of crypto protocols that are somehow permissive, and in return for runtime savings, occasionally make errors in these computations themselves? So to that end, I'll talk a little bit about this protocol that we've been looking at called Circa. Circa is meant to, yes.
We have a question in the audience if you want to jump in and ask.
Yeah, please, if you feel free to unmute and ask. Or
sure. No, I mean, I think the stuff is really, really impressive. I know you talked about doing a variety of architecture search, automated and other architecture search.
Yeah.
I wonder how automated you feel like injecting this kind of garbling or re-architecture could be, if and only if you detected you were part of one of these broadly distributed networks kind of thing. Or is this a technique that we should be evangelizing to all folks and just say, look, this is a better solution for you, whether or not you're in a broadly distributed network or not? Does that make sense?
I think the answer is you really do need to figure out the setting, because in fact, like the architecture search and redesigning strategies that we have been exploring in the plain text world, where you don't have client server, and in the plain text world, actually they incur a large cost as well. So I'll give you one example, right? So if you go back here, right, like there's this 4x blow up for our ReLU balance networks in the storage cost of, and if you're storing that network on your mobile device, you don't want to incur that 4x blow up in parameter count, right? So actually these networks, you're absolutely on target. I think these networks that we are redesigning, are just very fundamentally different, or at least have very fundamentally different properties, right. I would say, right?
Right.
Now, when you start looking at full system costs, actually there's ongoing work where we are looking at, how do I balance the two, exactly as you pointed out, right? And so that introduces new challenges and new kind of interesting problems.
Yeah, I don't
think of these as like diametrically opposite. Sorry, go ahead. Yeah.
No. I mean, this makes complete sense to me. I guess, we don't need to talk about it here, but I am looking for that future world in which we can abstract away the for better or worse, the infrastructure that something runs on.
Yes.
From the data scientists actually exploring a space.
Yes.
And if we ask them to say like, oh, I did have this network and it ran fine on my machine for better or worse, my 8 GPU machine. Ooh, I wonder how it would look to do it across 1,000 machines, at low priority. Ooh, that sounds very interesting. If we're asking them to then, spend a lot of time re-architecting, then they're probably not going to explore that, which would be a loss. But again, I totally understand. We can talk about it offline.
No. So that's a great point. And one of the things I'll point out is that we have, in parallel, this kind of project where we've been looking at what we call model switching, where essentially, I mean, again, machine learning is different from traditional workloads because you can train hundreds of different models for the same task, right? And each of those models can have different properties. And you can imagine a world in which you detect the scenario, in which you're operating, and then switch to the appropriate model that is optimized for that particular scenario. So I think that's a really good point. So briefly then, this is kind of recent work where we've been looking at, actually this goes back to the question that was previously asked about why are ReLUs so expensive? And as I pointed out, ReLUs are expensive because the Garbled circuit or GC protocols that are used to cryptographically compute ReLUs actually perform ReLU operations using Boolean logic gates by essentially converting that ReLU operation into a Boolean logic circuit. And this slide shows you exactly the Boolean logic circuit that is used for a typical Garbled circuit that computes a ReLU. So this involves two adders, you can see them here, followed by a multiplexer, a comparator, another multiplexer, subtraction, addition, multiplex, and a final multiplexer. The reason that you need this kind of large number of different, what a ReLU does is simple, right? A ReLU simply takes an input, compares that input against 0, outputs 0 if the input is negative, outputs the input itself if the input is positive, right? So you really think that all you need to do is you just need a simple comparator inside a ReLU. But it turns out that we're working, the inputs to the ReLU function come from a linear layer that is using a multi-party computation protocol. So essentially what you get are shares of the client's inputs. You get the shares of the ReLU's input in terms of YC and YS, which are the client share and the server share respectively. The first thing you have to do is to add up these shares. Then you have to essentially perform a modulo addition, right? Because you're working on floating point numbers and so on. So maybe in the interest of time, I'm not going to bore you with all the details, but suffice it to say that these Garbled circuits are fairly large. And in fact, each Garbled circuit per ReLU incurs a 17 kilobyte storage cost. This is per ReLU in the network, and there are millions of ReLUs in a typical deep network architecture. So can we reduce the size of this Garbled circuit somehow? And it turns out you can. The first simple thing you can observe is that a ReLU of an input X is no different than the input X itself times the sine of X, right? So instead of performing the ReLU operation using a Garbled circuit, you can perform only the sine computation using a Garbled circuit, and then use your traditional kind of multi-party computation protocols for multiplications, which are very inexpensive. So this automatically allows us to reduce our Garbled circuit size from the one shown on the left to the one shown on the right. You can see that Garbled circuit is smaller. And this is a functionality preserving optimization, and essentially incurs no additional errors, etc. But you can do something else as well. These computations that are happening inside the ReLU are actually field operations. In field operation, when you add two numbers, you have to compare against the prime, and if your addition exceeds the prime, then you have to essentially roll it back, right? So it's like a modulo addition, modulo a prime p. Now it turns out if you drop that modulo addition, you'll end up making errors in your computation. You're no longer performing the computation exactly, but the error rate, the fraction of times that your sine computation is incorrect, is proportional to the value of the ReLU input. So it's actually proportional to y, which is the input of your ReLU, divided by the prime itself. Now, if inputs to these ReLU functions were large, then you'd have a relatively high rate of faults. But it turns out if you examine traditional deep network architectures, most inputs to ReLU functions are small. And in fact, this fact has been used for a range of other optimizations. The fact that most ReLU inputs are actually small. So if you look at the distribution of Y, it's kind of heavily biased towards small inputs. And as a result, in practice, the actual rate of faults that are incurred in real-world neural networks with this additional approximation is actually relatively small, right? So that's one of the two optimizations that we perform. Additionally, what you can do is you can actually truncate the inputs that are provided as inputs to this network. And since you're now performing kind of arithmetic computations on truncated values, the size of these circuits reduces even further. But again, because you're truncating inputs, right, you're performing, say, I'll give you a simple example. Instead of comparing 0.125 versus 0, right, you'll be comparing 0.1 versus 0. Now, as long as the truncation is sufficient, as long as you're not truncating too much, you'll still be able to perform this comparison properly. But occasionally you'll make mistakes, right? If you truncate all the way to 3 bits, then you'll make mistakes occasionally. So this is the key idea. You can also do additional truncations of inputs to these ReLU functions that will add more faults, but those faults happen to be for only small values that are very close to 0. And again, if those faults happen only for small values close to 0, they don't really affect the output of the network very much. Okay, maybe I'll kind of skip the details a little bit, but essentially point out that if you look at inputs of a traditional or typical deep network, we're looking here at ResNet 18. These are the ReLU inputs on the x-axis. And this is a distribution of inputs, okay, from 0 to 2 to the power 26. And we truncate up to, let's say, 18 bits. You see that even truncating up to 18 bits, most of the values in the network are actually concentrated over here. You do incur relatively large faults for values that are below 2 to the power 18, but there are relatively few such values. And in any case, these are small magnitude values. So it doesn't really matter. The output of the network is quite resilient to these errors. And then for values above the truncation range, larger than 2 to the power 18, the fault rate is actually quite small. Okay. And once the fault rate does go up, it blows up for values that are close to 2 to the power 26, very large values, but then it turns out very few actual Ys fall in that range. So at the end of the day, if you really think about it, at the end, even though you're incurring faults in these computations, those faults don't really impact the accuracy of the network very much. We evaluated Circa, and again, I'm showing you the accuracy of the network on the y-axis as a fraction versus number of bits that we truncate. There are two kind of variants of Circa. I'll kind of ask you to ignore that. You can focus on the green line, and you can see that up to even 20 bits of truncation, there's really no change in accuracy. In fact, up to 18 bits of truncation, you get the same, right, modulo, very, very small changes. You get essentially the same accuracy as in the full network. Okay, and as a result, you can reduce runtimes quite significantly. So if I look at the base runtime, let's look at ResNet 18, which has a base runtime of 44.55 seconds. We can reduce that using Circa from 44.55 to 14.28, so roughly 3x reduction, with essentially no change in accuracy, with really very, very small reductions in accuracy. And what's interesting, what's nice is that these optimizations actually can be applied on top of other architectural search techniques like the one I presented before. In this case, we're actually applying Circa on top of an even improved architecture search technique that we presented at ICML in 2021. And you can see here that further improves or reduces runtime. So if you look at the net results, we are able to reduce runtime from the baseline of 44.55 seconds, for which we got 61% accuracy, to 3.21 seconds, for which we are again getting roughly 61.6% accuracy. So that's more than an order of magnitude reduction in runtime once you start applying all of the techniques that I've described to you on top of each other, right? So without any loss in accuracy. So that, I think, is one of the key messages I wanted to convey, which is if you start tailoring both the deep network architecture and the cryptographic protocols to the application domain, you can achieve these large benefits without compromising the quality of the application. So in this case, we are really, hopefully I've convinced you that we've really brought, 3.21 seconds per inference is by no means, practical, but I've hopefully convinced you that we have brought these cryptographic schemes a step closer towards practicality. I think you need another 10x somewhere to really make it practical and to really have these deployed in the real world. My goal was also to talk a little bit about work we've done on the integrity side, but in the interest of time, I'm actually going to conclude here and I'm happy to talk to people offline if they're interested in integrity type questions. But I'll stop here and kind of, again, conclude by saying that co-optimizing deep network architectures and crypto protocols, I think can bring tremendous value. And there's a space I'm very excited about and hope to continue working in. If there are people interested in collaboration, please reach out. And I know there are 3 minutes left, so I'll stop here and see if there are questions.
I mean, I think the work is tremendous and super relevant. We don't need to cover this now, but I'm working on a globally distributed compute framework that I think has a lot of overlap with this, and we'll need to figure out how to optimize training across that.
Yeah.
And certainly don't want to reinvent the wheel. So please reach out. I don't know who has who your point of contact is, but please do connect, and I'm happy to share it.
Absolutely, that'd be fantastic. I think training is an entirely, different beast, and really fascinating to think about how we could also optimize these for training. So yeah, I'd love to talk more.
Yeah, so I guess getting into that same question, it's like if you had a function that computed ReLUs, if we had the compute mechanism there, is that where you would try to, could you integrate the non-ReLU processing with hardware that does ReLUs?
Yeah, that's a really good question. I actually, my background is actually hardware, and so we have some ongoing projects where we're trying to implement some of these crypto protocols in hardware. My collaborator, Brandon Reagan, who I can also connect you to, is actually kind of leading that project right now. From my side, what I thought was most interesting in the few years we spent trying to kind of implement hardware for crypto to accelerate crypto was the use of high-level synthesis tools. So there's, high-level synthesis is an area that was kind of quite nascent when I was doing my PhD, but there have been massive strides in being able to take C code, for example, and directly convert it into logic gates. And if you're careful, right, you can actually, we've shown for certain crypto protocols with care, you can actually use HLS and get, hardware results that match even kind of handwritten RTL code. In fact, one of the big challenges in implementing crypto and hardware is, it's super complex and relatively easy to make mistakes, right? And sometimes difficult to pick up those mistakes. But if you have reference C implementations and you can directly go to gates, then there's an additional benefit that if you trust your C implementation, then you can have higher assurance in the resulting hardware as well.
Have you identified other bottlenecks, things like batch normalization or all these kinds of things?
That's an excellent point, right? So I go back to the training inference kind of difference. A batch norm during inference is actually just a linear computation. So actually during training, batch norm is going to become dominant, in fact, right? And so if I want to do training privately, then I have to worry about ReLUs, but I also have to worry about batch norms, right? And so we've been looking at training, for example, both inference and training for transformer architectures that kind of use these layer norms, right? There, in fact, even during inference, you have to do them. Like even layer norms are nonlinear computations. So do things like divisions and so on, which are complex.
Well, that was a really interesting talk and something I wasn't, expecting. I mean, as far as that topic. So thanks for sharing that.
Thank you.
Anyway, thanks everyone for joining. Thanks for watching. If you're watching online, if you want to know how to follow what we're doing, you can sign up for our email list in the footer. Let me take care of that. You can sign up for our email list in the footer at research.protocol.ai. You can follow us at Proto Research on Twitter, and generally keep an eye on our research blog. Send us an email at research@protocol.ai if you are interested in presenting any of your research in one of these talks, or if you know someone that you'd like to recommend. Thanks everyone, and have a great day, week, evening, whatever it might be.